ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you for tuning in. Today what we're going to do is we're going to take a look at stoichiometry. Now, stoichiometry, and that's how I pronounce this funny-looking word that's on the screen, is really not as bad as it seems. It's just a word that we use when we're going to tell somebody, hey, we're about to quantify. We're going to quantify something in chemistry. And so stoichiometry is the process in what we do and how we calculate and quantify things like, hey, how much of this do I need to react with this amount? How much product am I going to make in this reaction? What's going to be left over? Right? How much gas is this actually going to produce? How much energy is this going to give me? Right? So all these different kinds of things, we are going to use stoichiometry to actually be able to calculate and quantify. This is where we start transitioning from this abstract, analytical, what is an atom, what are the parts of an atom, and we actually start getting into the things that you would think of as chemistry, right? We're going to start mixing things together, be able to predict how much we're going to make, how much we need to use, and that kind of stuff, all right? Okay, so a couple of relationships that we do know, right, based on our knowledge of the mole and formula mass at this point, is we know that 1 mole is equal to 6.02 times 10 to the 23rd particles. All right, and so we know that, we understand that's Avogadro's number, and we know that that number is based on carbon 12. All right, we also know, based on formula mass, that 1 mole of a substance is going to be the formula mass. So if I have that amount of it, I've got 1 mole. And remember, this goes back to that point where I told you we are going to use the mole to quantify everything. Like that's our thing in chemistry, right, is the mole. Now, I am going to introduce a new one to you here, and the fact that 1 mole is equal to 22.4 liters of gas. And so if I have a gas and I've got 22.4 liters of a gas, so I've got a balloon that's holding 22.4 liters, right? That means I'm going to have a mole of that particular substance, all right? And so these three relationships right here are going to drive something that I'm about to draw on the screen, all right? So a couple of things. Here we go. Mole A. When I'm writing mole A, and ladies and gentlemen, this is going to be a rather large drawing, so even if you want to take your page and flip it sideways, make sure you get this thing big on the paper, all right? Draw it big. Okay, so there we go. We've got moles of A. So moles of A, so many of y'all are thinking about what A is. A is a variable, and it really is just the substance that I'm working with. So this is moles of substance A, all right? Now I'm going to draw a couple of arrows here. And notice all of the arrows are actually pointing away from the mole. And this is important. The direction of the arrow is important because when we set up this stoichiometry map that we're doing here, right, the direction of the arrow tells me to multiply. Right? If I'm going with the arrow, I am multiplying, and that's something, ladies and gentlemen, I would make sure that I get down. If I'm going in the direction of the arrow, I am multiplying. And so now these are my relationships. I've got particles of A. I've got grams of A, and I've got liters of A. All right? And so what are the numerical relationships there? Well, it goes back up to my three equalities up here. I'm going to use Avogadro's number, 6.202E23 there, right? My relationship between moles and formula mass is actually, or moles and grams is formula mass, and my relationship between moles and liters is actually 22.4. All right, and so those are those numbers, all right? Those are my relationships. And remember, at this point, you just need to understand if I'm going in the direction of the arrow, I am actually going to be multiplying. That means if I'm going in the opposite direction, I'm dividing. Okay, and so now what I'm going to do is I'm going to go over here, and I'm going to put moles of B. And so now the question becomes, what's the difference between moles of A and moles of B? Well, it's just a different substance. Whatever it is, it's just a different substance. So do my relationships still apply? Well, the answer is yes, right? I've still got those arrows now, but notice what I'm going to do with the center arrow is now I'm going to make it a double-sided arrow. So if I'm going from moles A to moles B, I'm multiplying all the time. Converting from moles to moles is always a multiplication, all right? And then the same relationships exist, right? This is still up here, particles of A, liters, these are B's, sorry, liters of B, particles of B, and then grams of B. My same numerical relationships still apply. 6.02 E23, so that's Avogadro's number. 22.4, and then formula mass. Now this is the formula mass of B, and I'm going to go over here and make that the formula mass of A. All right, and understand that we have to keep with our particular substance when we're going from moles A to grams A or moles B to grams B. Now this one in the center, I'm going to go ahead and come in here now, and I'm going to make this what I'm going to call a mole ratio. And we're going to talk about mole ratios here in just a second. But what I'm going to do now is I'm going to give you the rules for how to use this stoichiometry map to do stoichiometry. And it's really simple. There's only 2 rules here, ladies and gentlemen. Number 1, make a plan. Number 2, do the plan. Yeah, no, it's really that simple. Make a plan, do the plan. That's how we're going to do this. So, for example, let's say I've got a moles of A quantity. So I've got moles of A, and I want to know how many particles. So my question is, how many particles of A that is? Well, if I'm going from moles of A to particles of A, I'm going in the direction of the arrow, and I'm going to multiply by 6.02 times 10 to the 23rd. It's really that simple. No, really, it really is that simple. So I made my plan, I'm going to multiply, and then all I do is I take that quantity of moles of A and I multiply it by 6.02 times 10 to the 23rd. No, really, it's that simple. Make a plan, do the plan. That's all we're doing. Guess what? If I'm going from grams of A to grams of B, I'm going to divide by the formula mass of A, multiply by a mole ratio, multiply by the formula mass of B. It really is that simple, ladies and gentlemen. Please do not overcomplicate this. Now, stoichiometry, the way I teach it, becomes necessary or actually absolutely impossible if you don't commit the stoichiometry map to your memory. All right, so this is something that I do want you to remember. And now let's move on. Let's go ahead and explain what this mole ratio is. So, mole ratios. A ratio is in relation one quantity to another. So, the first mole ratio that we're going to look at is mole ratios based on subscripts. Now, mole ratios based on subscripts, I think I used sulfuric acid in my formula mass lecture. And so when we understand that my subscripts tells me our ratio, right? So in this particular case, I know that I've got 2 moles of hydrogen per 1 mole of H2SO4. So I've got moles of the particular element within the entire compound. All right, so that's my first mole ratio, and it's a ratio because it's a fraction, right? All of my ratios are fractions, and I'm just looking at the ratio of one element to what it is in the whole entire compound, okay? And so that's my first mole ratio, is based on subscripts. My second mole ratio is based on coefficients, and coefficients are what we see in these balanced chemical reactions. And so let's use a simple one. I'm going to do the combustion of hydrogen. So I've got 2 hydrogen plus, I think it's just a single oxygen, right? And it gives me 2 moles of water. Now, we do call these big numbers here, these are called coefficients. And if you don't know that, you need to notate that in your notes. So these are coefficients, and what they are is they are molar values. And so what this means is I've got 2 moles of hydrogen reacting with 1 mole of oxygen, because if there's nothing there, it's understood to be 1. So I've got 1 mole of oxygen to produce 2 moles of water. And so the mole ratios here is I've got a lot of them, but for example, I would say for every 2 moles of hydrogen in this particular case, I will get 2 moles of water. And so again, it's a mole over a mole, it's a mole ratio, right? And all I'm using is coefficients to come up with what that particular ratio is in terms of a balanced chemical equation or a balanced chemical reaction, all right? Another example that could come out of this is, for example, I have 2 moles of hydrogen. Let me go ahead and write that correctly. 2 moles of hydrogen, and I need 1 mole of oxygen to react with that. So that would be my mole ratio if I was trying to relate hydrogen and oxygen. And again, this is in that middle area, and this would be what I would multiply. This is my multiplier. That's what I mean by multiplying by a mole ratio, is I'm going to have my mole ratios there, and the kind of the fake it till you make it. If you want to come up with how you set this up, what goes on top versus what goes on bottom, the quantity or the substance that you want goes on top, and then what you're trying to convert from or get rid of goes on the bottom. All right, and that's kind of the fake it till you make it. You'll understand it's all based on dimensional analysis and canceling out these units. But for our mole ratios, what we want goes on top, what we don't want goes on bottom. All right? Okay, ladies and gentlemen, I know this was fast and furious. If you had any questions, hopefully you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class, and we'll do some practice with this.